let's get started with this. What I'm about to present is a virtual lesson that is hopefully going to serve you well as you're reviewing for the PreCalculus final exam, which is coming up. The topic that I'm going to focus on for the next 25 to 30 minutes is logarithmic and exponential functions. This is something that you studied first in Algebra 2. You learned some properties of logarithms, you've learned properties for exponents, and in PreCalculus we kind of up the rigor a little bit. Nothing crazy, but we're going to look at maybe some more advanced transformations of logs and exponentials. We're going to look at some trickier equations that need to be solved using properties of logarithms, and then we're going to end with an application problem. So let's move forward. Let's see how this goes. When I talk about an exponential function, I'm talking about a function where the exponent is actually the variable. In Algebra 1, you look at polynomials. You look at things of the form x squared. The variable is your base. The exponent is a constant. It's a number of some sort. When we're talking about exponentials, we're looking at functions of the form y equals 2 to the x. And just like we would have graphed back in Algebra 1, we would start by making a table of values, do an x and a y chart, and I'm going to select different values for x. So we'll say 0, 1, 2, and 3. But I also want to try negative values, so we'll have -1, -2, and -3. And then for each of these x values, I'm going to evaluate the original function at that point. So we'll start with an easy one. If x is equal to 1, then the corresponding y value is 2 to the first power. 2 to the first power is 2, so I'm going to have a point on my curve at the point 1, 2. If I let x equal 2, and I plug that in, I now have 2 squared. 2 squared is 4. The corresponding point on the curve is 2, 4. If x is 3, we get 2 cubed, which is 8, and you get the point 3, 8. And we can keep going forward. If x is 4, we get 2 to the 4th power, which is 16. So now we get the point 4, 16. If you pay attention to the points for this exponential, y equals 2 to the x, your x values are increasing just by 1. Every time I increase the x coordinate by 1, what I'm seeing is that the y values are actually doubling. When x is 1, y is 2. If I add 1 to the x value, I double the y value to 4. If I add 1 to the x value again, I'm now doubling the y value. It happens again, it happens again, it happens again. Now what about in the reverse? Let's plug in 0. 2 to the 0 power, well, anything raised to the power of 0 is 1. So now I have the point 0, 1. That's going to be the y-intercept for this graph. How about negative numbers? Well, 2 to the -1 is the same thing as 1 over 2 to the positive 1 power. That's a half. Now I have the point -1, 1/2. If x equals -2, 2 to the -2, that's the same as 1 over 2 squared, which is 1/4. I have the point -2, 1/4. If x is -3, we get 2 to the -3rd, which is 1 over 2 cubed. I have the point -3, 1/8. When I actually go and graph that one, let's start at 0, 1. I'm going to have a y-intercept over here at 2, 1. That point's been graphed. I now plot the point 1, 2. I go one space to the right, but now I go up twice as far, and I'm at 1, 2. Check. If x is 2, I go over one more space on the x-axis. I go up, there's 2, go up twice as high. Now I'm at the point 2, 4. 3, 8. Go over one more, go up twice as high. 4, 16. Over one more, go up twice as high. You can see graphically is that as I move slowly across the x-axis, I am increasing my y values by a factor of 2. So we're growing quickly. I could be evaluating the function at points in between 0 and 1. I could pick decimal numbers. I could pick fractions. What you're going to see is this upward trend from left to right. The function is increasing, and it's increasing quickly. This is why when we say something is growing exponentially, it's growing really, really, really quickly. Well, what about what happens with the negatives? If I go one space to the left, I only go up to 1/2. If I go to -2, I only go up to 1/4, only half as much as before. If I go over to x equals -3, I go up to 1/8. If I went to x equals -4, it would be a 16th. I'm going to get closer and closer and closer and closer and closer and closer and closer to the x-axis. The fancy word that we use for that is that is going to be our y. I'm sorry. Yeah, that is our. We have a horizontal asymptote. That horizontal asymptote is at y equals 0. So horizontal asymptote at y equals 0. My function will get closer to that horizontal line, but it's never going to touch. We have a y-intercept at 0, 1. We could also have conversations, if you'd like, about the domain and the range. The domain, I can evaluate an exponential for all values of x. I can do positive numbers as my exponent. I can have 0 as my exponent. I can have negative values in the exponent. So my domain will be -infinity to infinity. The range, this is where we want to be careful and pay attention to the graph. We can see that the graph is increasing. In fact, it's going to continue to grow towards infinity. We're going to go off the board really quickly. As I move to the left, though, as we head out towards -infinity, let's pay attention to what's happening with the graph. It's getting closer and closer and closer and closer to the line y equals 0, but it never actually gets there. No matter how large of a negative exponent you have, let's say you wanted to evaluate 2 to the -10th power. Well, 2 to the -10th power is the same as 1 over 2 to the 10th. 2 to the 10th is 1,024. 1 divided by 1,024 is small. It's really small. It's like dust, but it's still not quite 0. So even if I made this an even larger negative exponent, I would wind up having 1 divided by 2 raised to a large positive exponent. I'm never going to get to 0. I'll get close. I'll get infinitely close. That's why we call this a horizontal asymptote. And the range will be from 0 to infinity. That is our base case. That is our parent function, y equals 2 to the x. In this next slide, what I want to do is look at the parameters a, b, and c. I want to have conversations about what happens if instead of 2 for my base, I picked 3. What if I picked a small number? What if I were to pick a really large number? How does that impact the graph? We're also going to look at the impact of a. A is multiplying your exponential, so if you're really good at transformations, you know that a is going to cause a vertical stretch of the graph. C, if I'm adding C onto this whole thing, again going back to transformations, if I have a times b to the x, and I add C onto that, that is going to be a vertical shift. We can have all of the transformation conversations with this exponential function and with all the others. So let's move on to the next slide. We can see things maybe a little more dynamically. What you'll see for the next minute or two is going to be some graphs changing on the screen. Not so much me up here in front of the camera, but I'll be running the computer and hopefully speaking loud enough that we can all hear. Okay, so we're looking at a little program that I put together using Geometry Sketchpad. Really enjoy using Geometry Sketchpad for presentation purposes. It's a great way to look at parameters. What I've got here in blue is the function g of x, which equals a times b to the x plus c. We have another function that we're calling r of x, which equals 2 to the x. We just saw what that graph looked like on the previous slide. And I've generated the red curve, this exponential curve. That's this guy over here. It increases from left to right, just like my hand-drawn one does. It has a y-intercept over here at 0, 1, just like my hand-drawn one did. And what I want to do is I want to look at changing the parameters. the values for the parameters I have down here, A is equal to 1.01. I really wanted it to be equal to 1. I was not able to make the sliders get exactly equal to 1. We don't have to worry about that. B, which is my base, is equal to 2. C, which is the shifting factor, is equal to 0.01. Again, I was trying to get it close to 0, as close as I could. That was as close as I could get. Well, what I'm going to do first is we're going to show a new function. This one in blue is a times b to the x plus c. I'm going to go over to my slider, and I'm going to select different values for b. I'm going to, as I slide it to the left, the value of the base becomes smaller. As the base becomes smaller, and we know that it's becoming smaller because we can see that b equals 1.17, we want to pay attention to the behavior of the blue graph relative to the red graph. As the b value gets closer to 2, it bends up towards the graph y equals 2 to the x. If the base increases beyond 2, well, that means it's increasing faster. If the base shrinks, it gets closer to 1, what we see is it starts to bend away. Oops, sorry about that. It bends away, so it's increasing slower. It's still increasing left to right. If I could get it to be exactly b equals 1, there I am. What we have is actually no longer an exponential curve, but you have a line. And I'm struggling to get it to be exactly equal to 1. As my base continues to shrink past 1, what we see is actually a reversal of the behavior. Instead of the function increasing from left to right, the function is now decreasing from left to right. We still have a horizontal asymptote at y equals 0, but the graph is now decreasing. And the graph will continue to be a decreasing graph as long as my value of b is between 0 and 1. If I cross over into having a negative base, the graph disappears. There's all sorts of good conversation we could have about that. But at the end of the day, what I want everybody to have clear in their head is that if your base is a value between 0 and 1, the function will be decreasing from left to right. If b is equal to 1 exactly, it'll be a horizontal line. If the value of b is greater than 1, it is going to be an increasing curve. The larger the base is, the faster it will increase. All right, so before we leave the base, let's make sure that we're on the same page and we have a really clear understanding of the base. We're assuming that we don't have an a, well, our a value is 1, so we don't need to write it. Our c value is 0, we don't need to write it. We're just looking at exponentials of the form 2 to the x, some base raised to the x power. When my base is larger than 1, like what we're seeing right now in the blue, we're going to have a function that is increasing from left to right. If my base is a number, has a value between 0 and 1, the function is going to be decreasing from left to right. If the base is exactly equal to 1, it's a horizontal line if I can model that. We're not going to look at negative bases because the graph won't exist. But in all of these cases, whether my function is decreasing from left to right or it's increasing from left to right, the y-intercept remains at 0, 1. Well, why is that? If I have an exponential, so it's of the form b to the x, any base raised to the power of 0 will be 1, so my y-intercept is over here at 0, 1. Now let's look at the value of a. A is the number that we're going to multiply our exponential by. Since it's multiplication, what we should expect to see is a vertical stretching effect. And that is exactly what's going to happen. As my a increases, I'm stretching the graph vertically by whatever value a is. So there we go. If a is negative, well, not only is it going to stretch the graph, but because it's negative, we're going to reflect the graph. It's going to bend down. So it is now decreasing from left to right. The last thing for us to look at is the impact of c. Up until this point, the c, what we're adding to the exponential, has been equal to 0. If c is a positive number, that's going to shift the whole graph up, including your horizontal asymptote. We can see that the function no longer is approaching the x-axis. It is approaching another horizontal line as I go out further to the left. As we approach negative infinity, the graph will get closer and closer and closer and closer and closer to y equals, in this case, 5.45. If c is negative, you're going to shift the graph down, just like we did with lines and quadratics and sine functions. So let's summarize this. If I have an exponential of the form a times b to the x, the c tells you how you shift the graph up or down. The base is going to tell you if the function is increasing left to right or decreasing left to right. The a is your vertical stretch factor. When I'm graphing these on my own, I first look at the base to see what increasing or decreasing. Order of operations tells me to now look at the a. That'll tell me to do a vertical stretch or a reflection of some sort. Lastly, I look at the value of c, which is just going to be a vertical shift. That does it for graphing exponentials of the form a times b to the x plus c. What we're going to do now is we're going to look at some properties of logarithms. We'll look at what does it mean to ask a logarithm question, and then we'll solve some equations using properties of logarithms. So let's talk about the logarithm. The logarithm of a number, x, to a given base b, is the exponent by which the base must be raised to produce that number. What does that mean? Well, first of all, I get that from, it's just a standard textbook definition. What that means is if I have a number, we'll call that x, and I want to find the log base b of that number, what I'm really asking is my base raised to what power is equal to x. So another way that you can say that is the log base b of x is equal to y. That is the same thing. That is mathematically equivalent to asking the question, the base raised to what power is equal to x. Every logarithm can be transformed into an exponential equation, and then you can use your properties of exponents. Let's look at a few of these. I want to find the log base 3 of 81. What's the question being asked? The question that I'm asking you is 3, my base of 3, raised to what power, let's call that x, is equal to 81. This is one you can either just do it in your head, right? We know that 3 times 3 is 9, times 3 is 27, times another 3 is 81. So if 3 to the x equals 81, that means x is equal to 4. Now, what does that x equals 4 tell you? That tells you that the log base 3 of 81 is equal to 4. Done. Check it off the list. Move on to the next one. How about this one? The log of 1. It looks like I forgot to write the base. No, I didn't forget to write the base. This is a log that shows up quite often, so often that we don't bother to write what the base is. It's base 10. It's our common log. So in order to evaluate the log base 10 of 1, I need to ask myself the question, 10 raised to what power is equal to 1? That should be a quick one as well. The exponent has to be 0. 10 raised to the power of 0 is equal to 1. So x is equal to 0. The log base 10 of 1 is equal to 0. How about this next one? ln. What's ln? ln is the natural log. This is the log base e of e squared. So the question being asked, e to what power is equal to e squared? E to what power equals x squared? Another easy one. X equals 2. So the natural log of e squared is going to be 2. How about a decimal? The log base 2 of 0.125. I'm going to go over and write this on the side. We're looking at the log base 2 of 0.125. Before we do anything with this, we're going to transform it to the exponential version, which is 2 raised to what power is equal to 0.125. What I would do is I'd think back to middle school. We know the decimal 0.125 by another name. 0.125 is actually 1/8. 2 to a power equals 1/8. Well, if I'm going to have 8 in the denominator, that is the same thing as 1 over 2 cubed. I can rewrite this as 2 to the x equals 2 to the negative third power. So the x that I was after must be equal to negative 3. So the log base 2 of 0.125 is equal to negative 3. Check. Last one. The log base 7 of negative 49. The question being asked here is 7 raised to what power equals negative 49? Now let's be careful, because if somebody out there is thinking, oh, I know the answer is negative 2, 7 to the negative 2 power is the same as 1 over 7 squared. That's not it. There is actually no power that I can raise 7 to get a negative. 7 to the positive 2 power is positive 49. 7 to the negative 2 power is 1 over 49. 7 to the x equals negative 49 has no solution, so the log base 7 of negative 49 can't be done. It doesn't exist. That's actually going to help us when we start talking about the graph of a logarithm and then looking at domain and range restrictions. So just like we can graph exponentials, we can also graph logarithms. And so if I were to ask you to graph the function f of x equals the log base 2 of x, we're going to start by making a table of values again. And if I just randomly plug in, well, I don't want to randomly plug in some numbers. Let's strategically plug in some numbers. Let's start with 1. If x is 1, that means I need to find the log base 2 of 1. Based on the conversation we had in the last slide, the log base 2 of 1, the question I'm asking you is 2 raised to what power is equal to 1? Well, we already know the answer to that, 0. So that means the point 1 comma 0 is going to be on my graph. What about 2? The log base 2 of 2. What I'm really asking you is your base raised to what power is equal to 2? Log base 2 of 2 is equal to 1. I have on my graph now the point 2 comma 1. How about 3? The log base 2 of 3. 2 to what power is 3? Well, 2 to the first is 2. 2 squared is 4. I've passed 3. So the log base 2 of 3 is going to be somewhere between 1 and 2. I don't know exactly where it is, but it is going to be less than 2. Okay. How about 4? Log base 2 of 4. 2 to what power is equal to 4? 2. So now I've got the point 1 comma 0 on there, 2 comma 1, 3 comma something in between 1 and 2, 4 comma 2. As you start thinking strategically about the points that you're going to plug in, it's all going to boil down to, can I figure out the log base 2 of that number? Other ones you can find quickly without a calculator is the log base 2 of 8. Log base 2 of 8, 2 to a power is equal to 8, 3. I could also find the log base 2 of 16. The log base 2 of 16 is equal to 4. What we're going to find is that it is easy to find logs base 2 of 2 to a power. Well, how about 0? The log base 2 of 0, 2 to what power is equal to 0? That can't be done. This doesn't exist. You also cannot take the log base 2 or any base of negative numbers. So 0 is not going to be in your domain. Negative numbers are not going to be in your domain. What about numbers in between 0 and 1? Well, if I try a half, the log base 2 of a half, in order to figure that out, 2 to what power is equal to a half? Well, that'll be negative 1. Other ones I could do quickly, other powers of 2. Log base 2 of 1/4, that'll be negative 2. Log base 2 of 1/8, that'll be negative 3. Log base 2 of 1/16, negative 4. If you plot those, what you're going to find, let's start with 1, 0. You've got this point over here at 1, 0. you have the point 2, 1. If I go over twice as far, I go over to 4, I go up just 1 more. By doubling my x value, I increase the y value by 1. If I go out to 8, 3, there's 4, go out twice as far, now you go up 1 more space. 16, 4, I'd be off the camera. I'd go out twice as far and go up 1 more. My graph is going to increase like that. We've already said that you cannot take the log of a negative number, so we won't have anything over here in quadrants 2 and 3. If I were to take the log base 2 of a half, I get a negative value. Log base 2 of a fourth, a negative value. Log base 2 of an eighth, a negative value. What you're going to see is your graph is going to get closer and closer and closer to your y-axis. Your graph is increasing left to right. You now have an x-intercept of 1, 0. Instead of having a horizontal asymptote, you now have a vertical asymptote. Your vertical asymptote is over here at x equals 0. We can have conversations about domain and range, of course. The domain for the log base 2, your domain is going to start at 0 and go to infinity. Since I can't take the log of 0, that 0 is not going to be in the domain. I can't take the log of a negative number. That won't be in the domain either. If I want to look at the range, well, the range, my graph continues to increase as I go to the right. It continues to decrease as I get closer to x equals 0. The range is going to be negative infinity to infinity. Done. Piece of cake. All right, let's look at one more aspect of the log function, and then we'll just solve some log equations, and we'll be done with this video. All right, so let's look at the graph one more time. We're back to Geometry Sketchpad. All of this work over here on the left, I'd like you to ignore for now. In fact, you can ignore it completely. What I've graphed over here that you can see, this is the graph of y equals 2 to the x. What I want to graph next is the graph of the log base 2 of x. We've graphed these independently, but I wanted to graph them on the same screen so you could see side by side. This one up here, this function that is increasing from left to right, that is concave up, that is the graph of y equals 2 to the x. This graph over here is the graph of the log base 2 of x. It's also increasing from left to right, but it is concave down. Y equals 2 to the x has the point 0, 1 on there. Y equals log base 2 of x has the point 1, 0 on there. If I go over to where x equals 1, I would find the point 1, 2 on the exponential. I would then find the point 2, 1 on the logarithm. On the logarithmic version, sorry. If I plotted the line y equals x, which is now this dashed line, what you can see, or at least what I'm trying to illustrate, is that the graph of y equals 2 to the x, if it was reflected across the line y equals x, would give you the graph of y equals log base 2 of x. What does that really mean? Mathematically, it means that y equals 2 to the x is the inverse for the function y equals log base 2 of x. Now let's graph some other logs. What if I wanted to graph the log base 3 of x? That's the graph of log base 3 of x. That's the blue one. The graph is increasing from left to right. It still has an x-intercept of 1, 0, telling me that the log base 3 of 1 is equal to 0. We're increasing, but we're not increasing as quickly as the other one. The blue one is below the graph of y equals 2 to the x, but we are still increasing. I can now graph the log base 5 of x. That's this purple one. Passes through the point 1, 0. Approaches, as we get closer to 0, the graph dips down here towards negative infinity. As x approaches infinity, the graph is increasing, but not as fast as log base 2 of x did, not as fast even as the log base 3 of x. It's still increasing, but a little bit slower. If I were to then graph log base 10, log base 100, what we would expect to see is that as your base increases, the graph will increase slower and slower and slower. What if I wanted to graph a fractional base like the log of 1/2? Well, let's see. If I go and I plot that function, we still have an x-intercept of 1, 0, but instead of increasing from left to right, we are now decreasing from left to right. As we get closer to 0 from the left, the function is now increasing towards positive infinity.